Okay, good afternoon, everyone. Welcome again to Warsaw University Tuesday Astronomical seminar series. And today we have a speaker in person, Dominika Król from Jagellonian University. She's starting her third year of PhD and did her studies in Krakow as well. And she's going to tell us about microlensing, but from a different perspective, which is based on her recent paper. So, Dominika, the floor is yours. And I suggest you
Thank you very much for the invitation and the chance for giving this seminar. So I will focus today on the project which I recently finished, at least the main part of this project, which is the gravitational microlensing event in the optical light curve of active galaxy S50716. Sorry. So I guess introduction of gravitational lensing is not very necessary in details, especially in here. But let me start from the brief introduction, especially from the point of view of AGNs. So in general, gravitational lensing, we can divide in three main regimes: strong lensing, weak lensing, microlensing. And when it comes to AGNs, the most popular, the lensing regime which found the most application is always strong lensing. So for instance, here you can see a quasar HE0435, which is lensed, and you can see multiple images. The study of strongly lensed AGNs allow us a very special insight into the physics, especially of the inner parts. Then, of course, we have a weak lensing, which normally is in the context of galaxy clusters, and of course, the part which doesn't need to be introduced here, microlensing. And in microlensing, we mostly talk traditionally about galactic sources. And we can, in microlensing, we can see the change of the brightness of the source when the lens is going through the line of sight from the observer to the source. What is important is that this event will be achromatic. So in microlensing, we do not see multiple images. We see only the, we cannot observe multiple images. We only observe the magnification of the light curve. And it is used broadly in the galactic context, of course, for detecting objects which would be impossible to detect normally, for detecting exoplanets or massive complex halo objects. And in general, for the singular lenses, we have the magnification curve, which is this bell-like shape. For the exoplanets, we already have here the second body in the lens. So we have much less massive companion, which will introduce this kind of deviation to the magnification curve. But when we see binary lens, then the situation becomes even more complicated. So, as pointed out, for instance, by Mao and Kaczynski in 1991, we may expect that our lenses, in some cases, may be stellar objects which are in binary systems, since a lot of stellar objects are born in binary systems. And then, when the mass ratio is much higher than in case of exoplanets, the magnification pattern becomes much more complicated. And depending on the source trajectories, we can get the magnification curves which will deviate much more from this bell-like shape from the single lens. And transitioning to the AGN in the context of the gravitational lensing. So around 80s, 90s, in literature appeared the idea that maybe some part of the variability of active galaxies may be due to that lensing. So in general, especially blazars, so the AGNs which we normally observe, from the angle which is directed to the jet, they are very, very variable. So they are characterized by a variability for different frequencies, for different timescales, from hours to years. And there was an idea by Gopal Krishnan and Subramanian in 1991 that maybe achromatic optical variability of the blazars on our time scale may be due to gravitational microlensing of the relativistic jet nodes. Unfortunately, this idea didn't get much of the follow-up when it comes to observational work, mostly because of the technical issues, which I will touch on later on. But recently, in 2017, there was a paper by Benenham et al., which was analyzing the symmetrical achromatic variability due to gravitational lensing in the light curves of radio sources. So they were using monitoring programs at 15, 22, 37, 100, and 234 gigahertz. And using those data, they were trying to find candidates for the gravitational microlensing. So the most promising candidates which they selected, there were also some other sources mentioned in this paper, but the most promising candidates was J1415, the radio galaxy, radio blazar, which for 25, it was observed on those different frequencies for 25 years, and it showed 4-year-long U-shaped symmetrical achromatic variability events, as they called it, called SAPS later on. They can be seen here around 1993, around 2000, around 2009, and around 2015. And they decided to analyze the source to try to model it through microlensing. There were 2 papers by this group. First of them was from 2017. They, in general, they're hinted about this microlensing. They also made analysis using inverse ratio technique, and they were trying to fit observations with binary lens with some external elliptical mass surrounding this lens. Later on, they conducted much more detailed examination of this one source in 2022, recent paper, and they were trying to fit it in a much more by much more complicated fine tools, trying to use the best model using fitting or simultaneous fitting for different frequencies for all of these events together, and using also MuLensModel package. So they were able to fit all of the events with one single binary lens, with the mass ratio around 0.009 and separation around 1.15 of Einstein radius. So here you can see those fits for different events which I showed previously for different frequencies. And the question is, what is the lens in this in their context in the case of their work J1415? So they have a bit of a tricky situation because they don't know the redshift to the blazar. There is known spiral galaxy at Z around 0.25, but it's not sure if it's a host galaxy of this blazar. So they were they were analyzing two separate possibilities. That lens is located in the foreground, and it's in some dwarf galaxy, which is not detected optically differently than just through this lensing. Or that maybe the spiral galaxy is at this redshift 0.25 and blazar is behind it. Because in general, from the model form they fitting, they got the result that lens cannot be within the same galaxy as the radio source. It would lead to unrealistically high lens masses. So let me proceed to the object which we were interested in, which is the blazar S50716. It is a pretty special blazar because it has a particularly high duty cycle, meaning that on the short time scales, meaning that when we observe it during in the intra-night timescales, we will almost always see variability. And in general, it was, because of this, it was very often observed by some monitoring programs, including Whole Earth Laser Telescope. In general, for most of the blazars, the best we can get when it comes to light curves is few hours around now and then. It's never a very long coverage. The Whole Earth Laser Telescope was much better because they were using telescope around the Earth. And thanks to this, they were able to observe the object almost for a whole time for a few days. Of course, still, those are Earth-based, ground-based telescopes. So, for instance, bad weather may lead to some non-covered times. And then there was an absolute game changer, which is CEST. Of course, due to the fact that this is a satellite, it may observe the blazar no matter of the weather conditions. So we got the light curves, which have much better both the quality, the probing, and also they are much longer. The test data cover much longer time. So in general, what is important is that this blazar is unprecedented when it comes to data coverage. And this is also when I want to go back to the point from the paper 91, that they mentioned that we can expect that maybe some of the hours-long variability of the blazars may be due to the lensing of the jet, but it's very difficult to see it when we have, not for most of the sources, only hours-long coverage of the light curve. Okay, so the Whole Earth Laser Telescope observed this object many times, and some of them in 2003 and 2013 observed an interesting feature. It was noted by Bata et al. In 2016, and they mentioned that in this very highly variable source, they saw for about 6 hours, the source suddenly exhibited a strongly reduced level of diffract variability, resulting in a plateau in all 4 bands. So we have a chromatic change of the variability, and one of them can be seen here on this slide, around 100 on the x-axis. So you can see that in general we can see a high variability source, and then it goes. We get a plateau for around 7 hours. And we noticed similar events in the test data. So there are 4 month-long campaigns of the test data for the source, and we went through them and we found 4 other events which were very similar when it comes to the shape of the light curve. And here you can see the webbed and test events put together. Of course, we moved the magnitudes of all of the events to match the minimals. But as you can see, they last for a very similar amount of time, and also they have similar difference of the magnitude between the maximas and this plateau minimum. So, inspired by the previously mentioned work, we decided to try to fit it with microlensing. and we want to in general interpret this as a lensing of the precessing jet in the source by a binary lens. Oops, so the test data, the first season of observational season of test data, was also during that time, the Webb telescope also observed this blazar. And here you can see on the right the test coverage together with the points from different bands, different filters of the Webb telescope, Webb campaign. And from what we can see here, at least the parts of the minimas, which are covered also by Webb data, seem to be achromatic. The other thing which we can see here is also, of course, how much of a, how amazing is the data coverage of tests in comparison to even the best thing which we had so far, which was Webb. And for the Webb data, it would be impossible to identify this kind of behaviors for most of the coverage. So we started from, in general, exploring the possible magnification patterns which we can get from the binary lens. And we wanted to have, we thought that in general we would need a lens which for pretty high ranges of trajectories of the source of the magnification pattern can give us similar features. Since we have seen it 20 years ago, we have seen it in 2013, and we've seen it in 2019. So we started to explore lens parameter space, and in general, when we plot the magnification patterns, you can see that when we have a small, very small, the mass ratio, of course, we are going back to similar results as for the point-like lens. When we have small separation, in general, the magnification pattern will have a lot of features only in the center of it, in the very compact region. And when we start to increase both the mass ratios and the separations, we will be able to get much more complicated patterns. So we are moving to the right lower corner of this matrix plot. So we started a fitting procedure. In general, there are a lot of parameters which need to be fit, of course. So first of all, we have a time t0, the time of the closest approach. Then we have impact parameter, which is the trajectory parameter. We have the Einstein crossing time. We have the size of the source. We have the separation of the length of the binary. We have the mass ratio of the binary, and we have alpha, so the angle between the source trajectory and the binary axis. So we have 7 parameters to describe a single event. 3 of them should not change between the events. They should be the same, since they describe the binary length, and they describe source size seen from the lens. And 4 of them are the trajectory parameters. So they, of course, may vary from the event to the event. But it's impossible to fit all of the parameters at the same time. It's too much of the parameters. We didn't manage to do it. So we started from this exploring of the parameter space, so the parameter space of the lens separation and mass ratio. And then we started to use MuLensModel by Polensky and me from 2019 to try to fit the models, lens models to the Lightcurves. And we started by trying to find lens parameters which were able to model the all of the 6 events. And then we were performing, when we found the lens which was able to fit all of them, we were performing separate fits to fit the trajectory parameters. In general, still there is a lot of degeneration there. For instance, when we have for different values of TE, so the Einstein crossing time, we can get very similar fits when we only adjust U0 and T0. So, of course, they are not, especially trajectory parameters are not the only one possible. But in general, what we can see is that all of those events in the light curves of both tests, and also it is possible to fit with this model the web data, all of it is possible with one single binary length model. So our binary, which we fitted, has a Q, so mass ratio of 0.005. The separation is around 0.7 Einstein radiuses. And here you can see the trajectories which we chosen at the magnification pattern. So now we started to think, what is this length? So the constraint, so first of all, the length parameters, when we tried to calculate the masses, it became pretty clear that length has to be in the blazar host galaxy. So we have the distance between the lens and the source, much lower than the distance from the observer to the lens, and the distance to the source and to the lens from the observer point of view is similar. And then we can think about the constraints on the mass, or some constraints which will allow us to calculate the physical mass of the binary. So first of them is the fact that in blazars, we cannot expect emission regions to be smaller than the gravitational radius of the supermassive black hole in the nucleus. Second of them is that our lens must kind of cover, from our point of view, the center for at least 20 years, since we have seen the first event 20 years ago, and the last event we seen in 2019. So the velocity dispersion for this axis with light has to be, will give us some limitation on the size of the binary system. The other thing is that we can expect some maximal apparent velocity which we can observe for blazar. So for this particular blazar, the highest observed so far apparent velocity was 30, so beta equal 30 apparent velocity. So we assume that this is our maximum. And also the orbital period of the binary has to be much smaller than the time of the event, because it needs to be, the length to be stable through the event occurrence time. So from those four limitations which we were considering, the two most strict are the ones which discuss the maximal beta apparent velocity, maximal projected velocity, which was the maximal, as I mentioned, in this source ever observed was 30. And also the second one is the fact that for a typical blazar, in general, we expect velocity dispersion around 200 kilometers per second. So we can assume that we need to, the mass of the lens needs to fulfill those two inequalities. In this particular blazar, maybe I should also mention this, we don't know, there are no very accurate measurements of the supermassive black hole. So we assume here that we have a typical supermassive black hole for the blazar, which is around 10 to the 8 of solar mass. And from those two limits, we arrive with the possible mass lenses, which of course also will depend on the distance between the lens and the source. So when we assume that the distance between the lens and the source is 100 parsecs, we will get very high, of course, masses from 10 to the 6 to 10 to the 8 solar masses. But then here, as you can see on the plot, when we will move the length to around 10 kiloparsecs, so to the edge of the, so for a much higher distance in the galaxy, we will get from 10 to the power of 4 to 10 to the power of 6 solar masses. So our length may be consistent when it comes to masses to intermediate black holes, which is accompanied by the lower mass object. In general, our fitting would suggest that there is a very small mass ratio in the binary, but there are some n-body simulations of globular clusters, which first of all lead to the creation of intermediate black holes, and secondly, most of them are have companions which are much less massive. And this kind of mass ranges are expected. The LISA laser interferometer space antenna is expected to see mergers of the objects of this kind of mass ranges around 2 per year. So just to mention that it's not those are the mass ranges and the mass ratios which are in general discussed in the literature. So thank you very much for your attention.
Thank you very much. We have plenty of time for questions and discussions. People here in the audience first.
Excuse me, could you show me the slide with this radio curve?
You mean from the work?
Yes, yes. This is the same galaxy.
No. This is completely different galaxy. I just want to discuss the literature of the Microlensing in the blazar. In the blazar.
You mentioned that you have observations from 20 years.
They have. It's like this paper which I described, which is Vanderham et al. 2017. They were looking for the observations from 20 years for different radio galaxies, and they arrived with, I don't remember exactly how many, but some other also candidates for having the microlensing events. But this one was the most apparent, and this one was also the most, it appeared many times. So they decided to focus on this one. But this is completely different galaxy, and this is just a project which of others from literature, which I just wanted to mention to, give you the picture of, in general, of the lensing of the active galaxies.
But you mentioned that your object was observed for 20 years.
This object, my object.
Estimation of
So this one is, in general, this is a completely, so the time scales of those radio variability are much longer. So they are able to just observe it, let's say, once, I don't know, once a day for a moment, once a week. I don't remember exactly what was the frequency. But when we have this kind of optical variability, we are able to observe it only for a short period of time. So we have just a small pieces of the light curves at different times. And of course, in whole Earth blazar telescope, we can expect to have it for a few days, but in general, it won't be that frequent. And what I mentioned is the first time we can see this kind of feature was in 2003. So if we interpret it as this gravitational microlensing, we need to be able to get it for 20 years, because 20 years ago was the first time. And now, okay, 2019, so it's maybe, it's a bit less, but we have to be able to still get it. So the lens has to be in the given position.
Yeah, so just to follow on this, so do you have a radio light curve for your object, which is on similar times?
No.
No, but that would be something.
It would be very interesting, but yeah, unfortunately.
Yeah, because if you show you have the same behavior same time scales in optical and radio.
No, the time scales are different here and
so these events, they look different in radio.
For those first objects, the totally different object from literature, those are lasting for about 1 year.
Right, but do they have similar optical counterparts?
I don't believe they have optical observations at this kind of scale, because as I just mentioned, it's very difficult to get it. I don't.
So this object was observed in radio, but on different wavelengths,
on
right?
different
and they
frequencies.
see the same,
Yes.
but no optical.
No
Your
optical.
object is
Only
opposite.
optical.
We only have optical, we don't have radio.
We don't have radio, we just have different filters, and for what we can see in different filters of optical wavelength, it behaves the same.
I see. Okay, makes sense. 11.
So I was wondering about the physical nature of a secondary object in a lens. So let's assume the intermediate black hole has a mass of, I don't know, 1,000 solar masses. Then it means that the secondary is 200 times less massive, right? Which is then 50, right? Am I right? Yes. So what could that be, and why the intermediate black hole doesn't affect the secondary in the way that we see it in the model? Because we see 4 times the same shape, right?
Okay, so when it comes to what it can be, when it comes to what it can be, so when we made the search of the literature, we found those n-body simulations, which mentioned that in globular clusters in general, we can expect that when we have evolution, we can get, first of all, through merger intermediate black hole, and when they made the simulations, most of them would end up as also in the binary with other stellar mass black hole in this kind of binary. When it comes to why it doesn't change, I'm not sure if I understand the question properly, but you asked why for 20 years this system is not changing, or
yeah.
So what? So we were thinking about it, and the answer, which, in my opinion, answer is that first of all, when there is an orbiting of the secondary mass, what it makes with the magnification patterns, it will rotate it. So in general, we may expect that the differences in the trajectories may cancel out those changes. And second part is that we also, when we would have different events, they would look totally or completely differently, but maybe in all of this mess of the red noise of the blazar, there are also other events. We just can see them when they have this very characteristic pattern, and we don't see if they cut this magnification pattern, for instance, in this direction. So just in the horizontal, in this direction, right, in Y direction. So maybe we just cannot then identify them in this very messy emission of the laser in general.
So you assume the binary is kind of sitting on top of the equator. It's just rotated off axis.
Yes, yes.
To the
This
right
one
side,
has to
and
be,
then you have these tiny caustics crossing later.
Exactly. Yes.
I know. So you kind of can have an idea about the period, maybe.
Yes, we would, but the issue is again that we don't have a coverage form between. So we don't know, for instance, if in 2010 we could maybe have observed very similar events.
Well, you can predict the next one.
Yeah, this one is possible. Yeah.
So what are your plans for this object?
So yeah, it would be for sure nice to have a future Lightcurves to be able to identify it, to maybe be able to see how often it appears, maybe in different energetical ranges. But yes, so maybe we hope for another data patch for this one.
So I want to understand you have just one model and you rotate it, yes? And it's got the
Yeah, so in general,
goes out of caustic and back to caustic, yes?
yes, so we have one lens model, so one binary, the same mass ratio, the same separation, and we get we can obtain those magnification curves by first just rotating, yes, exactly, just in different trajectories.
Okay, and I have another question about the monochromatic of that. Isn't the spectrum of the blazars are not flat?
So in general, you can, so people observe the variability, which does not, which is different for, so when we have variability and flares, in general in blazars, we can normally observe them in different frequencies and they appear in different times. So it's not, it's absolutely not sure that all of the variability should be happening the same for different filters. For instance, here you can see, this is a very small plot, but here you can see that for sometimes the red part, so our filter is on the lower part, and sometimes it's the highest part.
Okay, but my experience, so I do spectroscopy of such flares, and sometimes they are blazars, and in this blazar I usually got the flat spectrum without any features. Sometimes there are intergalactic absorption.
So it depends, but for instance, for those observations, for the whole part of the observation, they saw the differences in the different filters, and for this part, it was completely flat. But before, it was not. So maybe it depends, but it's not sure that they will be flat. And here we can see a difference between before and during this feature.
So there are two sources of variability, right?
Yes, of course. All of it is.
And on top of that.
Yes.
So it means that your
microlensing
event is also affected by
exactly, of course.
Right?
So of course we have very high input variability of the laser, and also the issue is that since it's red noise variability, it's very difficult to even predict if those features are. There is no possibility. I mean, it's very difficult. There are no mathematically described specific methods to deal with it and to deal if it's actually this. So yes, of course, this is the issue that we will have both in string and this variability.
Cool. Any more questions, comments here? In Zoom? Okay, so let's thank our speaker. Thank you.